The great book of nature is written in the language of mathematics. If we really take that profound idea from Galileo Galilei as our guiding light today, then we absolutely have to understand its specific dialect for describing change.
And that dialect? It's the differential equation. Simply put, it involves an unknown function together with one or more of its derivatives to describe exactly how a quantity changes. Instead of just telling us where things are right now, these equations focus on how things are moving, evolving, or reacting over time. It's literally the difference between staring at a static photograph and watching a dynamic, living movie unfold right in front of you.
So, welcome to this explainer on the language of nature, decoding differential equations, drawing on the work of Dr. Rosalina Ba. Our central philosophy today is what we call motivation before mechanism. We aren't just going to stare at abstract math on a whiteboard. We're going to dig into the fundamental why behind the math.
Here is our mathematical roadmap for today. 1. The language of change. 2. Classifying the equations. 3. The first-ordered toolkit. 4. Scaling up to systems. And finally, 5. Applications in the real world.
Okay, let's jump right into part 1, the language of change, motivation before mechanism.
In applied mathematics, we study these equations to solve very visceral physical problems. Picture a piping hot, 100 degrees Celsius cup of coffee slowly cooling down in a 20-degree room. Or think about the invisible steady rate of radioactive decay of a substance. Or even a falling body fighting against the drag of air resistance. See, it's often way easier to describe how these quantities are changing than it is to describe the quantities themselves directly. Each of these scenarios is basically just a statement about change, and by translating these physical laws into math, we can predict exactly what's going to happen next.
Moving on to Section 2, classifying the equations, which is essentially the grammar of change.
Before we can actually solve anything, we have to understand a problem's mathematical DNA. On one side of the ring, we've got ordinary differential equations, or ODEs, which depend on a single independent variable. On the other side, we have partial differential equations, or PDEs, and those depend on 2 or more variables. Now, to keep our learning super focused and efficient today, this explainer is going to focus entirely on ordinary equations with a single variable. Let's keep it simple, right?
We also really need to contrast linear and nonlinear equations. Linear equations have the unknown function and its derivatives appearing to the first power only. Nonlinear equations, on the other hand, well, they contain products, powers, or transcendental functions of the unknown function. Basically, linearity just restricts how the unknown function is allowed to interact with itself. Think of it as a predictable straight-line relationship. Nonlinear equations, they allow for these messy, unpredictable loops. It is a crucial distinction because it tells us exactly which tools in our toolbox we're allowed to use to solve them.
That brings us to Section 3, the first-order toolkit. I like to call these hacks for reversing change.
We are definitely not doing tedious mathematical proofs today. Instead, we're looking at clever, practical hacks to reverse engineer rates of change and uncover our unknown functions. The first major hack is the method of separation of variables. It's a really elegant 3-step recipe. Step 1, write the equation in the form dy over dx equals f of x times g of y. Step 2, divide by g of y and multiply by dx. You physically separate the variables here. You shove all the x's into one corner and the y's into the other. And then step 3, simply integrate both sides. It is a beautiful, straightforward method, and it's used for solving things like the exact half-life of radioactive materials or predicting population growth.
But what happens when variables stubbornly refuse to separate? I mean, life isn't always that neat, like in complex fluid mixing problems or tricky electrical circuits. Well, we use a workaround, the integrating factor method. Step 1, write it in standard form. Step 2 is where the magic actually happens. You find this magical multiplier called the integrating factor, mu of x. Step 3, you multiply the whole equation by it, which elegantly forces the messy left side to become a perfect exact derivative. And finally, step 4, integrate and solve. Boom, problem solved.
All right, Section 4, scaling up to systems, complexity and coupling.
We are scaling up now. When we move from a single particles motion to highly coupled, complex systems where multiple things are interacting all at once, think interconnected tanks of brine or massive electrical grids, we need a powerful diagnostic tool. Eigenvalues are exactly that tool. Just by calculating them, you can determine a system's entire destiny. Real eigenvalues of the same sign, they create a node. Opposite signs create a saddle. Purely imaginary eigenvalues give you a center, meaning closed periodic orbits. And complex eigenvalues with a real part, they create a spiral.
It's kind of mind-blowing, actually. It's like being able to read the geometric future of a system from just a couple of numbers.
We see this profoundly when we look at damped harmonic motion. By listing these three types, overdamped, critically damped, and underdamped, we see exactly how tweaking just one variable completely alters physical reality. Think about your car's suspension hitting a bump. Is it overdamped and super rigid? Is it critically damped, so it smoothly and rapidly returns to level? Or is it underdamped, leaving you bouncing wildly down the road while slowly losing energy? The math literally dictates the physical ride.
And finally, Section 5, Applications in the Real World, the grand finale. Let's completely immerse ourselves into the geometry and physics of the world around us. Picture a heavy chain hanging between two posts. It could be a massive suspension bridge cable or even just a simple silver necklace draped over a jewelry stand. Ask yourself, what is the exact mathematical shape of that hanging chain? What invisible mathematical forces are dictating its precise curve?
The answer is the catenary curve. It is the precise curve formed by a flexible, inextensible chain hanging under its own weight, and it is perfectly described and solved via this specific second-order nonlinear differential equation. This is such an incredible, beautiful example of how abstract, nonlinear math directly dictates the tangible shape of an everyday physical object.
And honestly, the applications are everywhere. These equations govern the flow of electricity in RLC circuits according to Kirchhoff's laws. They determine exact escape velocity thresholds, allowing us to calculate whether a rocket fired from Earth will actually escape gravity entirely or just plummet right back down. They define orthogonal trajectories that map the invisible force fields of our physical world. From the swing of simple pendulums to the dynamics of complex ecosystems, these equations are actively governing the hidden rules of our universe. So, I'll leave you with this final, provocative thought for our explainer today. Now that you know how to read the mathematics of change, where else is it operating completely unnoticed in your daily life? I guarantee you, if you look closely enough, you are going to start seeing differential equations absolutely everywhere. Keep observing, keep learning, and thank you so much for joining me today.